Guess the word. Yes, you're right. Motion. In this lesson, you should be able to have 75% level of competency in the following desirable learning objectives. 1. Define the basic keywords and key concepts related to motion. 2. Formulate the equations of motion using the basic key concepts. 3. Apply the formula and concepts in solving physics problems related to motion. 4. Evaluate the results of the problem solving if it conforms reality. Let us define motion. One definition is, motion is the phenomenon in which an object changes its position with respect to time. Motion is also defined as the change in position of an object with respect to its surroundings in a given interval of time. There are general types of motion. We have rotary motion or circular motion, a special type of motion in which the object is on rotation around a fixed axis like a figure skater rotating on an ice rink. Another kind of motion is the oscillatory motion, sometimes called as periodic motion or reciprocating motions, otherwise known as simple harmonic motion, abbreviated as SHMs, a repeating motion in which an object continuously repeats in the same motion again and again like a swing. A repetitive and continuous up and down or back and forth motion like a needle in a sewing machine. Oscillatory motion would keep on moving forever when there is an absence of friction, but in our real world, the motion eventually stops and comes to an equilibrium. Motion can also be classified according to the number of directions involved. We have the linear motion, a one-dimensional motion on a straight line, like an athlete running on a straight track. Followed by the two-dimensional motion. Two-dimensional, 2D, motion means motion that takes place in two different directions, or coordinates, at the same time. One example of 2D motion is the projectile motion. We also have the three-dimensional motion. Motion in space, which incorporates all the x, y, and z axis, is called three-dimensional motion. Just like the movement of electrons in the atom and the movement of the gyroscope. A good look on the classification of motion is shown below. We can start describing motion using the elements involved in motion. First, we try to differentiate distance from displacement. Distance is defined as the total distance covered, while displacement is the total directed distance covered or traveled from the initial to final position. Distance is a scalar quantity while displacement is a vector quantity. In this slide, we will calculate for the total distance traveled along the perimeter of the rectangular court. We see that point A is 10 meters away from point B is 20 meters away from point C. If you are going from point A to point C, by passing through point B, you have traveled a distance of 30 meters. You can get this by adding the lengths of the segments. But, if we are asked to find the displacement from point A to point C, we need to draw a straight line from point A to point C and the measure of this directed distance, and it is the displacement from point A to point C. We use the Pythagorean theorem to solve for the length of the directed distance or the displacement from point A to point C. We see that you can start from the same position and stop somewhere else, yet you will have a different value of distance and displacement. We realize that distance depends on the path traveled, but displacement only depends on the length of a straight path connecting the initial and final position of the object. Another element of motion is time, and it is defined as the duration of events or motion. It is measured in seconds. We can compare two runners in a racetrack. We can quantify our observation on who's faster using speed. Speed is the ratio between the distances covered per unit time. If you have traveled greater distance in a small fraction of time, that means you are fast. It has a formula given by S for speed. S is equal to distance divided by time, or S is equal to d over t. Velocity is another term related to motion. Velocity is a vector quantity that refers to the rate at which an object changes its position per unit time. Velocity, quantity that designates how fast and in what direction a point is moving. A point always moves in a direction that is tangent to its path. Velocity is the directional speed of an object in motion as an indication of its rate of change in position as observed from a particular frame of reference and as measured by a particular standard of time, e.g. 60 km per hour northbound. The symbol used in place of velocity is lowercase v. Velocity is equal to displacement over time. Or if the motion happened along the x-axis. We can say that there is a change in the coordinates along the x-axis and this change happened over a period of time. We say that velocity, v, is equal to delta x divided by delta t, or x sub 2 minus x sub 1 all over, t sub 2 minus t sub 1. For those who know their algebra, this formula is just like the slope of the line. During a trip, the velocity of the car changes. We may wish to know the average velocity during this trip. We may not know the values of intermediate velocities, but we can determine the initial and final velocity. We divide it by 2, and that is how we get the average velocity. Another concept related to motion that we experienced in our daily lives is acceleration. Acceleration, denoted by lowercase a, is a vector quantity and is equal to delta v all over delta t. This is also equal to final velocity minus initial velocity all over final time, initial time. This is our equation 5. From equation 5, we can try to find the final velocity after the object has undergone acceleration. We cross-multiply delta t to the left-hand side of the equation, giving us a times delta t is equal to final velocity minus initial velocity. We can solve for the final velocity and it is equal to v sub f is equal to v sub I plus a times t. This is our equation 6. We can use equation 6 to modify equation 3, which is the formula for average velocity. The formula for the final velocity from equation 6 is to be substituted to the final velocity in equation 3. We have average velocity is equal to v sub I plus v sub I plus a times t all over 2. We can simplify this as 2v sub I plus a times t all over 2. We find that the average velocity is equal to v sub I plus the quantity of a times t over 2. Equation 7 can be equated to equation 2 to find the final position of the object after it experienced acceleration. We have delta x over delta t is equal to v sub I plus the quantity of a times delta t over 2. We multiply delta t to both sides of the equation and we get delta x is equal to v sub I times delta t plus the quantity of a times delta t squared all over 2. We can solve for x sub 2, and we find that x sub 2 is equal to x sub 1 plus v sub I times delta t plus the quantity of a times delta t squared all over 2. This is our equation 8. Free fall motion. The Earth pulls all objects towards its center through its ever-present gravity. The gravitational force of the Earth causes objects to be accelerated towards its center. The value of the acceleration due to gravity is negative 9.81 meters per second squared. When a body is dropped from a certain height above the ground, meaning it was not thrown and its initial velocity is 0 meters per second, it is under the effect of Earth's gravitational pull and the object is now free falling towards the center of the Earth. The object's velocity will gradually increase according to the formula of final velocity along the y-axis is equal to v sub I along the y-axis minus gt. The object will then interact with the Earth's atmosphere and will experience atmospheric friction, otherwise known as air drag. Air drag or atmospheric friction will cause the object to reach its terminal velocity. Distance traveled by free-falling bodies. We can use the formula in rectilinear motion to calculate for the directed distance traveled by free-falling object. We can do this when we make the following changes. The table below shows the variables used along the x-axis and y-axis and its quantity being described. All the variables along the x-axis will be changed into y. We can now modify the formula for motion along the x-axis as, remember that the directed distance along the x-axis is equal to initial velocity v sub x times time plus 1/2 times a sub x times t squared will be transformed to d sub y is equal to initial velocity times time minus 1/2 g t squared. Assuming that the object starts with an initial velocity of 0 meters per second. The formula above will be d sub y is equal to negative 1/2 g t squared. This is the formula for finding the directed distance along the y-axis if the initial velocity is equal to 0. This formula is used to find the displacement. In this case, the displacement will be the same as the distance traveled by object since there is only one direction of motion and this is towards the center of the Earth. You can imagine that this is a straight line. The table shows the displacement of the object from the origin after t seconds when dropped from a certain place. On the table shown below, in first column, each row shows time t is given in seconds. In the next column, the values of the displacement in meters has negative sign because it is moving away from the origin. In third column, each row reveals the value of the velocity along the y-axis in meters per second. Gravity is ever present and it means that it is acting on all matter. Objects that are thrown vertically upwards are not exempted to the pull of Earth's gravity towards its center. The motion of the object, particularly its velocity, will gradually slow down before it reaches its maximum height, where it momentarily stops in 0 meters per second. We have here the formula for final velocity, which is v sub f along the y-axis is equal to the initial velocity minus gt. At the maximum height, final velocity is equal to 0 meters per second. We can solve for the time it takes for the object before it reached the maximum height. We see that our new equation is t up is equal to initial velocity divided by g. To show the ever-present effect of gravity on all objects, we analyze the behavior of an object thrown vertically upwards with an initial velocity of 15 meters per second. Consider the table below. We can infer from the table that the final velocity of the object as it goes up is slowing down and eventually it stops. When it stops, the object is now solely acted upon by gravity and will fall towards the center of the Earth, with an increasing velocity, but having opposite direction, hence the sign will be negative. The amount of time of an object in upward motion or t up is also equal to the time that it will take to fall down or t down. Since the time to get up is equal to time to get down, the total travel time is t total is equal to 2 times t up, or t total is equal to t up plus t down. Maximum height reached by the object. Any object thrown vertically upwards will eventually and momentarily stop when it is at its maximum height. The final velocity at its maximum height is equal to 0 meters per second. We can solve for the maximum height, or h max, reached by the object by using the formula. Maximum height reached by an object is equal to d up is equal to v sub I along the y-axis times t minus 1/2 g t squared. We use the value of t up for time t in this equation. So, maximum height reached by an object, h max, is equal to d up is equal to v sub I times t up minus 1/2 g t up squared. The formula above can be simplified even more by using t up is equal to v sub I divided by g. Now we have the maximum height reached by an object is equal to d up is equal to v sub I squared divided by 2g. Sample problem. An object is thrown vertically upwards, has an initial velocity of 15 meters per second. Find the maximum height reached by the object. Solution. We can use the formula that we have derived earlier to solve for the height reached by this object. We have here, initial velocity along the y-axis is equal to 15 meters per second. We can use maximum height, h max or d up, is equal to initial velocity squared, divided by 2 times g. Plug in the values to the formula. D up is equal to v sub I squared, divided by 2 times g. H max is equal to 15 meters per second, raised to the power of 2, divided by 2, times 9.8 meters per second squared. Simplify. Now we have the value for the maximum height reached by an object, which is 11.479 meters. Finding the velocity of an object thrown in mid-air when it is at a certain height. The object is thrown vertically upwards, so it has an initial velocity. We currently do not know the time at which it will reach the given height. The equation, maximum height reached by an object is equal to d up, is equal to v sub I along the y-axis times time t minus 1/2 g t squared needs to be modified. We will eliminate the variable for time and write it in terms of the initial and final velocities of the object. Height reached by an object is equal to d up is equal to v sub I along the y-axis times t minus 1/2 g t squared. We remember that. From here, we can see that time t is equal to. We will expand the terms in the parenthesis and then gather all similar terms to simplify the equation. Get the LCD, which is equal to -2. After simplifying the equation, we see that final velocity along y-axis is equal to the square root of initial velocity squared, minus 2, times g, times the quantity of y sub 2, minus y sub 1. Sample problem. Calculate for the velocity of an object thrown vertically upward with an initial velocity of 15 meters per second when it is 5 meters above the building where it was thrown. Solution. Final velocity along y-axis is equal to the square root of initial velocity squared, minus 2, times g, times the quantity of y sub 2, minus y sub 1. Plug in all the given values to the formula. Simplify the given equation. Get the square root and it gives us the answer of final velocity along y-axis is equal to 11.269 meters per second. Today we will study projectile motion. Visit our website ytuniversity.ph for more science topics. Projectile motion is a motion that happens in 2 dimensions. The object called as the projectile travels along the vertical axis and hence have a vertical component. The vertical component is affected by gravity. It is also an observable fact that the object, or the projectile's shadow, is moving parallel to the horizontal axis, and hence we proved that it has a horizontal component. Direction of a projectile motion. The projectile is projected at an angle theta. We can get the component velocities of the projectile using this angle and the trigonometric function. We use the sine function to find the vertical component, while the cosine function is used to find the horizontal component. The interaction between these components produce the path traveled by the projectile, which seems to be an arc of different lengths. We also note that each velocity component has its characteristics. As you may have guessed, the y component has a changing velocity and hence indicates the presence of acceleration. The x component has a constant velocity behavior. Here are the important notations that we should be familiar with when deriving the formula for projectile motion. These notations have meaning or concepts behind them. They are as follows. The initial velocity is also called muzzle velocity, is read as v sub o. The x component is read as v sub x, which is equal to v sub o cosine theta, is constant all throughout the course of motion. The y component read as v sub y is equal to v sub o sine theta, is changing in magnitude and direction. The angle theta is constant all throughout. At the same height, the velocity is equal but different in direction. We also note that the time it takes to reach the maximum height is equal to the time it takes for the ball to go down. As mentioned earlier, the y component is affected by the acceleration due to gravity. This requires us to use the free fall concepts that we have learned from our past discussions. We need to know the initial and final velocity component along the y-axis using the sine function. We also remind ourselves that the velocity of an object thrown in mid-air at its peak will be equal to 0 meters per second if solely acted upon by gravity. We plug the formula to the free fall equation and we can get the amount of time t that it takes for the projectile to reach its maximum height. We have time to get up is equal to v sub o sine theta over g. We may wish to know the maximum height of the projectile above the ground. We take note that the amount of time it takes for the ball to reach its maximum height is equal to the time it will take for the projectile to fall back to the ground. Hence we can use the free fall concept to get the height using the value of time to get up. H, or d, is equal to positive or negative 1/2 gt squared. The sign depends on the orientation from the origin or reference frame of the observer. But since we are talking about the height, it will be positive. We substitute the expression for t up, then simplify the formula and we get initial velocity along the y-axis raised to the power of 2 all over 2g. We can also use the other formula to derive for the maximum height. And arrived at the same answer. We now solve for the range of the projectile. The range is the distance traveled along the x-axis. We can use the fact that the time to get up is also the amount of time to get down. Hence the total time interval of the projectile motion is time to get up plus time to get down, or 2 times the time to get up. We also use the fact that the velocity along the x-axis is constant. We can use the formula range r, or d, is equal to v sub x times total time. Then we realize that this is equal to v sub o cosine theta times 2t up. This can now be simplified as r is equal to v sub o squared times sine 2 theta all over g. That's pretty much everything that you have to learn about projectile motion. If you like to learn more about science concepts, then click the subscribe button, hit the notification bell to get updated when we post new contents. See you next time here in the YD University.